Assalamualaikum and very good evening. We are from Group 6, which is V Engineering. We'll explain to you about the production of ethanol for our plant design project. So the reaction involved is hydration of ethylene, where the reaction occur is at 229 degrees Celsius with the pressure of 50 atm in the presence of zirconium tungsten as catalyst. The raw material is ethylene and water itself, where the ethylene feed needed is 28,965 kg per hour, while water feed needed is 31,034.48 kg per hour. And based on material balance, the production of ethanol is 4,755.05 kg per hour. So the design include process control, process safety, wastewater treatment, process optimization, heat exchanger network, mechanical design and equipment sizing, equipment costing, and also economy analysis. So this is the process flow diagram for our plant design.
So now let's look into process integration. In simple words, process integration is a technique to improve planning and design of a plant by reducing the nominal and operating costs. So in this project, we will focus on heat integration to determine the feasible HEN to minimize the usage of external heating and cooling. So as you can see here is our process flow diagram for the ethanol production, and based on the figure, we have exactly 2 heaters and 3 coolers. So we are using problem table algorithm PTA method to do the pinch analysis. All the temperature values required, Ts and Tt, are tabulated in this table. We set 20 degrees Celsius as delta T minimum, and all the hot stream temperature values are subtracted 20 to get the Ts adjusted and Tt adjusted values. The FCP values are obtained from Aspen HYSYS. Based on the Ts adjusted and Tt adjusted, we arrange all the temperatures from highest to the lowest, which is 210 degrees Celsius to 5 degrees Celsius. And then we match the stream from H1, H2, H3, C1 and C2. Then we calculate the delta T, delta FCP so that we could obtain delta Q. Then we start with delta Q equal to 0 to obtain the most negative value, which is negative 608 and 83. From there, we will obtain the T pinch cold and T pinch hot, which is at 73 degrees Celsius and 93 degrees Celsius respectively. So now, let's look at stream matching. In this figure, you can see streams are labeled in purple color, and below them are the values of CP of respective streams, while in green are the values of energy in a particular stream. So let's look on the right side first. The rule is CC must be greater than CH, so the only streams that obey the rule is stream H1 and C1. So stream C1 will transfer all of its energy to H1, but the energy is not enough. At about 64 degrees C, it will need about 1800 more energy. So we added a cooler to further cool down the stream. While on the left side, the rule is CH must be greater than CC, but there is no stream obey the rule. So we are splitting H1 to match it with C1 and C2. So all the energy transferred between those streams are labeled in blue. So based on the stream matching, we have 3 lines that connecting the streams, which means we are going to have 3 heat exchangers. So this is the new process flow diagram. We have added 3 heat exchangers into the process flow.
Greetings, I'm Kohan and I will be explaining on the process optimization. Generally, the common goal of optimization is to maximize profitability, reduce costs, or increase the operating efficiency of the process in the plant. Typically, main branches of optimization are from different perspectives: treatment optimization, operating procedures optimization, and the control optimization. Optimization is known to maximize the profit gain while it is worked in a way to minimize the capital cost and the operating costs. Optimization is a tool to maximize our profitability by minimizing the supply of raw materials and maximizing the product. In this case, our target that we want to maximize in the production of ethanol which is 11494.80 kilo per hour, and our supply that we want to minimize it is the ethylene, which is initially set to 28965.52 kilo per hour, depending on the stoichiometric coefficient of ethylene ethanol, which is 0.609, and water ethanol, which is 0.391. This is a stoichiometric table for ethanol production. So there are few steps in this process optimization. First is step 1, which is define decision variable. So we label P1 for amount of product, which is ethanol, P2 amount of reactant, which is water, R amount of reactant, which is ethylene, Z is maximum profit. Then step 2 will be the define objective function. As can be seen, the max profit function. Then step 3 is defining equality and inequality constraints. First, the inequality constraints. Ethylene supply R must be less than 28965.52 kilo per hour, while ethanol production P1 must be more than 11494.80 kilo per hour. While equality constraints, which is R equals to 0.609 times P1, while P2 which, which is 0.391 times P1. So the followed by non-negativity constraints, which is R, P1 and P2 more or equals to 0. So final step will be the step 4, the optimization technique done by using solver add in Microsoft Excel. So finally, after optimization, the maximum profit is near to the manually calculated, which is 4 which is RM 46076.02 per hour. Thank you.
Greetings to the panels. I am Joshua Luis, and I'm going to explain about the equipment sizing and mechanical design about our project. So, we have done the sizing of equipment really in details, as this part is important in order to proceed to the economic analysis and mechanical design. The sizing was done based on Chemical Engineering Volume 6 and Product Design Principles 3rd edition. So in this section, panels will notice that we are selecting and designing the equipment based on available standard British standard, the ASTM standards. Next. All right. As you can see, this is our process flow diagram, PFD, for the ethanol production. Based on this PFD, you will notice that there are 12 equipments consist of one mixture, one reactor, one compressor, one troll valve, one pump, and one heater, two cooler, three distillation columns, and one heat exchanger after we have done the heat exchanger integration. So, I will go through in a glance for each of the equipment specification sheet. As the conclusion of proof, you may refer to the report that we have attached also. Okay, so first thing first, I will explain about the first part in this section, which is the equipment sizing of our production, of our ethanol production. The first one, sizing equipment of mixture. These are the this is its specification. As you can see, these two is the data that we have taken from the expand HYSYS. And for the mixture, for the equipment of mixture, the material we are using is carbon steel. Instead of stainless steel, we are using carbon because mixture only does the mixture does not require more like criteria for mixing. So instead of stainless steel, we are using the carbon steel, as carbon steel also more affordable or more cheap rather than compared to stainless steel. The next one is the reactor sizing. Okay, this one is the specification sheet, as you can see. So for the reactor itself, we are using stainless steel for its material of construction, and the value that you can see is based on the calculated one. The next one is the compressor. Compressor is necessary as it is one of the criteria for the materials before it goes to the reactor. The pressure need to be increased. So previously, some of the panels comment our project that we are advised to use staging instead of compressor, but we have looking further for advice from another lecturer that expert in the sizing of equipment also. Then the expert said that using compressor also much more reliable, as it is more cheap, better than doing the staging one. The next one is the pump. These are the equipment specification. As for the calculation part, you may refer to our report that we have attached. This is the heater one. Before this, we actually have two heater, H10, H100 and H101. But after we have done the integrating of heat exchanger, we reduce one heater and we add up one heat exchanger. So this one is the cooler for C101 cooler DC. There are three distillation columns in our production of ethanol. This one the second one, this one the third one. Right, this one is the heat exchanger that I have mentioned just now, that we particularly need to add up, and it is necessary to balance the heat transfer, the heat flow. So basically, for the sizing equipment for our project, there are 12 equipments, and these are the conclusion. For the calculation part, you may refer to our report. And the next one, I will explain about the mechanical design. Let's proceed to the next part, which is the mechanical design. So we have decided we will put three equipments in this mechanical design, which is the first one is mechanical design of reactor, the second one mechanical design of distillation column, and the last one mechanical design of the heat exchanger. So first of all, for the drawing of the design, I myself learning it through the online seminar provided by Chemical Pure Engineering previously, plus with the initiative of learning through a book called Chemical Engineering Volume 6. And also I refer to the YouTube. I am using AutoCAD as the application to draw the drawings. For the calculation parts, we as a group learn it by exchange opinion with other group and with the guidance of senior who works as engineer. So let's take a look for the first part. On the left side, as panels can see, These are the mechanical design specification sheet for the adiabatic reactor, and the right side is the mechanical design drawing of it. So these are the information provided to the to refer to be referred in these drawings. So how we get these values, I will explain. First thing first, what we have done is we find the design pressure, we find the design temperature, and then both of these to be used and to be checked on the chemical engineering volume, so that find we can determine what is the type of the material construction. So basically the material construction is stainless steel, and then we find the corrosion allowance, we find the welded joint efficiency, and then we find the minimum wall thickness. The minimum wall thickness is, after considering as what has been stated here, you put the value into the equation, and then we calculate, and then we find this is the value, and it is bigger than 9. So we decided to take this value instead of 9, because it cannot hold the vessel. And then as this value is already provided on the table. And then we find the head enclosure, we put all the values into the equation, and we find this value as what has been stated on the table, on this table here. Then the next one, we find the weight load, we find the weight of the catalyst, we find the wind loads. All these steps we are referring based on the book, on the chemical engineering volume 6. And then we find, after we find the weight of the cylinder vessel, the weight of ethylene, and the weight of the catalyst, we total it up, and then we got this value. This value is represented at here at the table. And then next we find the bending moment, and we got the value. This value we are already on the table also. And then we find the analysis of stress. Here got analysis of stress. Oh, wait this value, then this value is used to find the value at the bending stress. Actually there is a question over here, but we only simplify it, so we don't want to make it long. Then we got this value, it's already on the table, and we find the upwind, the downwind, and to be specific, to be satisfied, we draw the box. So as we can see, either it is below the maximum allowable design or not. And finally we determine the vessel support. As what has been stated here, stainless steel has been chosen again for the material type for the skirt. And this last statement, what it means is, here all the value, and all this value is taken on the book. That's why this 1 2 3 4 5 6 7 8 here. So that's all for the first one. All right, moving to the next equipment, which is mechanical design of distillation column. So this is the specifications sheet for it. These three columns, and these are the drawings of the distillation column itself. Okay, so this one is the smallest version. It's not even smallest lah, but it's like a better version of this. When it is zoomed, and you will see the like the measurement here. Okay, so how we got these values on the specification sheet is, it is the same as what I have explained the previous equipment, which is the reactor. here. It all the same. We refer based on the book as what the book stated. There, there, and finally we got here all the equation already provided, and we only put all the values into the equation and we calculated it, and we consider what we need to consider, and we put the reasons and the observation, the suitable one, until we find the steps. So the third equipment would be the mechanical design of heat exchanger. Okay, the third one, it differs a bit um with the two equipments that I already mentioned. So this is the mechanical design specification, and this is the drawings, as you can see, and this is the what we call the tube that has been illustrated, but it is not possible. It might be different from the calculated one lah, just only for the illustration purpose. So the how we got this value is this is the condition lah, the condition of the plant, and based on this condition we got the data specification, because based on the book it is like refer to the table, and then we got the value, and once we got the value we managed to find the tube side, the shell side, and so on. And it is based on this also, right? Why we choose one shell, two tube passes? Because um it suits to our production, and we have done our research, and it really does. So that's all for me for the mechanical design part. Thank you.
My name is Hanif. I will continue this presentation on equipment costing. First, we will look into the costing of mixer. The power consumption P is 0.307 kilowatt. The design type is agitator mixer based on figure 5.42. CP 1982 is 3000. Escalate price using CE Plant Cost Index for 2000. CE Index for 2000 is 476.6. CE Index for 1982 is 315. Then the CP 2000 we will get around 17,000 ringgit. For carbon steel bare module factor is 2. So the cost on bare module is 34,000 ringgit. Next is the costing of reactor R100. First, calculate the base cost CB, which is $12,574. Find added cost CPL for platform and ladder, which is around $796,000. Next, find the total purchase cost of a packed bag reactor with material factor 2.1, and then the total purchase cost is around $822,000. The bare module cost with bare module factor 4.16, and the cost is around $3.4 million. For the costing of compressor, the assumption is Material factor is 2.5. Drive type factor 1.15. CE cost index 550. CE cost index constant is 500. Then calculate for the NM, PC, and then we'll get the base purchase cost, which is around $2.2 million. The total cost purchase is $6.5 million, and the cost per module is $14 million. Next is the costing of pump. This is a pump costing calculation example on P100. First step, calculate the base cost, and then you'll get base cost around $12,000. Second step is to calculate the purchase of pump, CP, and the CP is around $24,000. Motor costing calculation example on pump 100. First step, calculate the base cost, and the base cost is around $12,000. Second step, calculate the purchase of electric motor, and the CP is around $16,000. Proceed to the costing of heater on heater 101. First step, calculate the base cost CB. CB is around $600. Second step, calculate the purchase cost. The purchase cost is around $1,300. The third step is calculate purchase cost on bare module, and the cost per module is around $2,000. Next is the costing of cooler on cooler 101. First, calculate the base cost, and the base cost is around $2,000, and calculate the purchase cost CP. CP is around $2,000. Next, we continue on costing of distillation column. This is the example calculation on DC102. First, calculate the vessel cost. We assume that the weight is less than 9,000 pounds. Then we take the weight is 8,500 pounds. Then we calculate the vessel cost, which is around $49,000. Next, we calculate the platform cost, CPL, which is around $7,000, and the FNT is 1, FTT is 1, and FTM is 1. Next is the calculation on CBT. CBT is around $900, and then calculate the CT. The CT is around $18,000, and we got the purchase cost is around $75,000. This is the summary of equipment costing. The total cost on heat exchanger is around 200,000 ringgit. The total cost on distillation column is around 1.9 million ringgit. The total cost on pump is around 49,000 ringgit. The total cost on compressor is around 56 million ringgit. The total cost on reactor is around 56 million ringgit, and the total cost on mixer is around 34,000 ringgit.
I am Nur Agnes, and I will discuss about the wastewater management in our ethanol production plant. Wastewater are categorized as three main types, which are biological, chemical, physical, with the same purpose on removing the pollutants from the industrial waste or municipal waste. The main objective of this wastewater management is to minimize and decrease environmental pollution, especially for those plants that consist toxic components. Waste treatment is also an important process because it can ensure the environment are not affected by the plant. This wastewater management are essential to maintain a good condition of the ecosystem. Wastes are usually present in four types of states, including the solid, liquid, gas, or mixture. However, there is some standard that should be followed to limit the level of the chemical residues or the waste that could possibly lead to environmental concern. By regulating the standards, environment can be ensured to reduce pollution or harm that can be caused by the excessive waste. I will discuss the waste management steps that was taken by our ethanol production plant. First is by planning the facility, second is by designing, third is by the special studies, final design, then value engineering, then construction, 7 is by the startup and operation, 8 is by environmental regulation and wastewater standard in Malaysia that we have to follow, and 9 is the wastewater standard in Malaysia that we done some research for our ethanol production plant. There are ways to prevent pollution and waste minimized from the stream. First, it can be improved by process, technology, and equipment. Plant operation can also be improved to prevent pollution. Potential waste can be also recycled, and last can be redesigning or formulating the end product. This is the wastewater standard in Malaysia based on DOE on 2010. It can be seen that standard A and standard P should be followed for wastewater. Next is profitability analysis. So the total capital investment of this plant is at least RM 750 million and total production cost at least 190 million, and cash income CRA after tax is at least 17 million, and the plant spent at least 3 years for startup, and its operating life is at least 15 years.
Assalamualaikum and good evening. My name is Rushda and I will explain to you about the process control in the plant design. And for cooler and heater, the control and measure variable is based on temperature of the outlet stream. But for the manipulated variable, it's based on flow rate of cooling water for cooler and heating water for heater. The set point for cooler is at temperature 25 degrees Celsius, but for heater is at temperature 200 degrees Celsius. For compressor and pump, the controller and measure variable is based on pressure of the outlet stream, and the set point for compressor is at 50 atm outlet stream, and for pump is at 1 atm for outlet stream. The mixer for control and measure variable is based on the flow rate of the outlet stream, and the manipulated variable is the rate of raw material and water inlet, and the set point for the mixer is at total flow rate 68,788 kg per hour. And for the reactor, the set point for the reactor is at temperature 229. For distillation column, this set point is based on the part in the distillation column itself. Different part of the distillation column will have a different set point. So this is the process controller PNID for each equipment, which is cooler, compressor, pump, heater, distillation column, mixer, and reactor. Next, we move on to process safety. For plant safety, which is hazard that affect the plant safety which come from the external factor, which is fire, overpressure and underpressure, spills and leak, tank rupture. To achieve the stability of the plant safety is by doing inherent safety, which is include pressure relief valve, emergency valve, interlock system, and non-return valve. Hazard study is purposely to reduce the hazard in the plant, which is we need to identify the parameter, possible causes, possible consequences, and action required. So this is basically the rough idea to undergo hazard in the plant. So plant startup, which is firstly we need to operational checkout, instrumentation checking, which is using hydrostatic testing, final inspection of vessel, verification of alarm and trips. The third one is by using line flushing and cleaning, instrument tally and inventory list for startup, and finally we will use final equipment preparation, which is dry out and boil out, catalyst loading. And finally, for plant shutdown, which is we need to plan. Other than that, unit feed and temperatures are slowly decreased. Unit balances and piping are de-inventored to recover all unit hydrocarbons. We need to purge with inert gas, check the LEL of each vessels, check the vessels daily for LEL, and lastly, we will final inspection before equipment is closed up. And for the conclusion is, we have considered all the aspects to build the plant, which is the plant design for the production of ethanol by using hydration of ethylene will give the total capital investment TCI of this plant is 738,800,952 and 60 cents, and the total production of cost, which is TPC, is 193,220,476 and 80 cents, and the net annual cash income CI after tax is 73,201,288.84 cents. The plan is spent for 3 years for startup, and its operating life is until 15 years. Thank you.